Section 8.1 Part 2, Distribution of the Sample Mean. Lesson objective: describe the distribution of the sample mean samples from a population that's not normal. If you recall from the last video, we learned that the mean of the sample means is equal to the population mean. And we also learned that the standard deviation of the sample means is actually smaller than the population. How much smaller? By this formula here. The population standard deviation divided by the square root of n. So as n increases, the standard deviation of the sample means decreases. In this video, we're going to look at populations that are not normally distributed. The following table and histogram give the probability distribution for rolling a fair die. So there are 6 faces on the die. Each has an equal chance of happening, 1/6. So each of these probabilities are the same. If you were to calculate the mean for this distribution, it turns out to be 3.5, and the standard deviation turns out to be 1.708. This is what the histogram would look like, and each of these numbers have an equal chance. This is what we call a uniform distribution. So this population is not normal. Estimate the sampling distribution of X bar by obtaining 200 simple random samples of size 4 and calculate the sample means for each of the 200 samples. Repeat for sample size n equals 10 and 30. Histograms of the sampling distribution of the sample mean for each sample size are given on the next slide. This is what it looks like when the sample size is 4, roughly bell shape, and notice that the mean is close to the population mean, 3.5. For sample size of 10, notice the standard deviation decreased. The mean of the sampling distribution looks like 3.5, same thing as the population mean. And if we look at the sample size of 30, we see the standard deviations even decreased even more, and the mean of this distribution is equal to the mean of the population. So let's summarize. This is one of the most important theorems of all of statistics. It's called the central limit theorem, CLT for short. The mean of the sampling distribution is equal to the mean of the parent population, and the standard deviation of the sampling distribution of the sample means is sigma divided by the square root of n, regardless of the sample size. What the central limit theorem states is the shape of the distribution of the sample means becomes approximately normal as the sample size n increases, regardless of the shape of the population. Now, what this means is any population, no matter what shape, skew left, skew right, bell shape, uniform, any shape of the population, the distribution of the sample means coming from that population will be normal as the sample size increases. So you may ask, well, how big does n have to be? Well, the rule of thumb is for sample sizes that are 30 or more, the distribution of X bar will become approximately normal. Let's look at a visual. Here we have the parent population. A is being normal, B is what we call a reverse J shaped or even a negative exponential, and the last one is C, a uniform distribution. If we look at the sampling distribution of X bar for sample size of 2, we see that for the normal distribution, sampling means is normal. This one's becoming more normal. This one looks like a triangle. If we increase the sample size to 10, we see a pattern here. And if we look at 30, notice all the means are the same. And notice the standard deviation decreases as the sample size increases. So the central limit theorem states that any population, no matter what the shape, the sampling distribution of the X bars will become normal for sample sizes 30 or more. Let's look at another example. This is the relative frequency histogram for household size. So here, this is what we would call skew right. Here's the number of people, so we have 1, 2, 3 to 7. Now this is the histogram for the sample means for 1,000 samples of size 30, and it's superimposed with the normal curve. So even though the original population was skew right, the distribution of the sample means becomes normal. Let's do an example. Based upon past records, the mean time for an oil change at Horn's 10-minute oil change is 11.4 minutes, with a standard deviation of 3.2 minutes. If a random sample of n equals 35 changes is selected, describe the sampling distribution of the sample mean. Well, since our sample size is 30 or more, no matter what shape the original population has, we know that for the distribution of the sample means, it's going to become approximately normal. Its mean is going to have the same mean as the population, 11.4, and the standard deviation is going to get smaller. We take 3.2 and divide it by the square root of our sample size, 35. This is our standard deviation for the sampling distribution of the sample means. We call this the standard error. Part B. If a random sample of n equals 35 oil changes is selected, what is the probability that the mean oil change time is less than 11 minutes? We know the distribution of this. We know its mean. We know its standard deviation. So the first thing we want to do is draw a picture. The mean is 11.4. We want what's the probability that the mean oil change time is less than 11 minutes. And we do our z-score. We take our x, 11, minus the mean, 11.4, and we divide it by the standard error. We end up with a negative 0.74. Looking up at negative 0.74 in table 5, we get a probability of 0.2296. So in conclusion, the sampling distribution of the sample mean. The mean of the x bars equals the population mean. Here's the notation. The standard deviation of x bar equals the population standard deviation divided by the square root of the sample size. It's always going to get smaller. If the random variable x is normally distributed, x bar, regardless of the sample size, will be normally distributed. If the sample size is large, our rule of thumb is n equals 30 or more, x bar is approximately normally distributed regardless of the distribution of the random variable. So any population shape will become normal. Thanks for watching.